Right. So next, the fifth one. So here we have to use proposition 818 to prove corollary 819. This is the proposition that we proved in the previous video. So we may already remember its statement, but still, because we are again going to use it, so let's recall it briefly. In it, we have a function f from the set of natural numbers into any set y. Then the image f of n is at most countable. We have to use this to prove corollary 819. So its statement also we are going to have to recall. So here the statement is this: let X be a countable set and f from X into y be a function where y, of course, just like before, some set. Then the image f of X is at most countable. This thing. So that means it's almost like this one, but instead of having the set of natural numbers, here we have a general countable set X. Okay, so let us now see the solution. So what is it that we are given? We are given two things. One is that X is a countable set, and the other thing is that there is one such function. So because X is countable, by definition there will be a bijection between X and N, and we are going to use that fact to start our solution like this. Since X is countable, there exists a bijection G from N onto X. Okay. Now, in order to be able to use this proposition, we need a function whose domain is the set of natural numbers. And well, we already have one such function, but that will not work. We have to take the composition of f and g, and we next write like this: applying proposition 818 to the function f composition g, which maps n into y. Yeah, it really maps n into y, because this f is not this f, we are talking about this f, because g will first of all take us from n to x, and then f will take us from x to y. So f composition g takes us from n to y. This image hence is at most countable. And we now just need to note that this set is nothing but f of x itself. F composition G of n is equal to f of G of n by definition of composition f of G of n, but note that G is a bijection, so G of n must be equal to x. That's because being a bijection, G is onto, it's surjective. So that's how we have proved that f of x is also at most countable, and here the solution ends. Let's see the next one. Eight, 1, 6. Let A be a set A is any set. Show that A is at most countable if and only if there exists an injective map f from A into n. From A into n, again the author has written, but it's understood, from A into n. So this is a necessary and sufficient condition for a set to be at most countable. That means we have to prove two things, and among them, let us first of all assume that we have one such function, and let us first show that A is at most countable, and then we will prove the converse. Solution. Assume that there is an injective map f from A into n, then the map f from A into f of A is a bijection. Why? That's because you see, when we have an injective map and we change the range, keeping in mind that the outputs of the function are also there in the new range, then if our original map is injective, then this new map also naturally it stays injective. But now, because we have replaced n with f of A, it is additionally surjective also, it's onto also, and that makes it a bijection. So that means A and f of A will have the same cardinality. But note that f of A is naturally a subset of n, and we already know that any subset of n is at most countable. So f of A is at most countable, and as a result now that we have this bijection, A would also have to be at most countable. So that's how we will get one half of our claim. Since f of A is a subset of the set of natural numbers, this is at most countable, and the result we are using here is corollary 816. So A is also at most countable. A is also at most countable, but precisely how is A at most countable, and how are we concluding from the at most countability of f of A that A is at most countable? You divide it into two cases. Say your f of A is finite because it's at most countable, so either it is finite or countable. If f of A is finite, then because we have this bijection, so A would also have to be finite, and in fact these two sets should have the same number of elements, which however is not important now. Now the fact is that A then becomes finite. That's what matters. And when f of A is countable, then there is a bijection between f of A and n, but then you can use that bijection and this bijection. You can take their composition to show that there is a bijection between A and n, proving that A is countable. So A is either finite or countable, and that is why A is at most countable. Now conversely, let A be at most countable. Now just like that, we have two cases, either A is finite or it is countable. If A is countable, then by definition there exists a bijection f from A onto M, and this bijection is of course also an injection, that means an injective map. Clearly F is injective, and that's what we want. We want that such a map be there. If on the other hand A is finite, then there is a then also there is a bijection between A and a finite part of N. then there is a bijection. Let me call it, say, H. From A into this set, the set of all natural numbers such that 1 is less than or equal to n and n is less than or equal to the cardinality of A. In fact, this bijection comes from the definition of the cardinality of A itself. This map naturally gives rise to an injective map H from A into n. So again we have got one such injective map. And why are we saying that this is natural? It's like this. You have A here and you have your this set here. If I am calling this set, say, B, then you have B here. But you can clearly see that B is a subset of n. And we have this map H. So all we are now doing, because this one also we are calling H, it may seem a little strange. Strictly speaking, we should not call this map H because it is really not this H. The ranges are different, but everything else is same. That's because you see, what we have is that we are not changing the rule of the function H. It still is H. Whatever elements of A are being mapped onto whatever elements of B, that still continues to be like that, but we have just simply changed the range n. Now because our original H is 1 to 1, so this also remains 1 to 1. These additional elements that we have, we will definitely have additional elements in n because B is finite whereas n is infinite. They do not affect this one-to-oneness in any manner, so this becomes injective. In fact, not just one-to-oneness, our original H was bijective also, but now we have got injectivity and never bijectivity. That's because this is finite whereas this is, the entire n is infinite. In any case, we have maps like this. Okay, so assuming that A is at most countable led us to the conclusion that one such injective map exists from A into the set of natural numbers, and that completes the solution. And let me end the video here itself because I think too long videos are too difficult to watch fully. So our next upload is this coming Tuesday, and we have already gone through which are the things we have already gone through. Group theory we have done, field theory we have done, then calculus also we have done. So this coming Tuesday let's do vector spaces, and then of course we can go to number theory, graph theory, those things. So with that I wrap things up. So see you on Tuesday with vector spaces. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.